Hello, everyone, and welcome to the next lecture on computer vision. In the last lecture, we finished image sequence processing, and concretely, we discussed the Kalman filter for 1D, but also briefly for higher dimensions, and we saw what all the Kalman filter is about, because we want to do state estimation, and we have noise in the measurements. Plus, we work with continuous variables. That's the essence of the Kalman filter. We looked at a few small other things around image sequence processing, and then we did the Outlook chapter. We looked at 3D vision, generative adversarial networks, and vision transformers. Today, we will look into the foundations of mobile robotics, because quite some of you have chosen to pick a robot so far because you will work on a robot vision project. Not all of you, some of you will work on different projects. And that's why I will provide a foundation or an introduction to the foundations of mobile robotics today, which once this is done, we will actually talk about the projects and the timeline for the coming weeks in this course. So, if you have taken a robot from the lab, many of you have got one that looks something like this. And this platform is actually based on Jetson, which is a GPU, and from NVIDIA. And based on that, they offer NVIDIA offers the chatbot platform, which uses the Jetson GPU and puts a mobile robot around it. And the package looks something like this. If you got it and you need to assemble a robot on your own, some of you who got a robot may have it already assembled. And once you assemble it, it looks like this. It's a mobile robot. It has antennas for connecting to Wi-Fi. It has a GPU from NVIDIA. It has 2 wheels, plus a camera and a couple of other features. There were other robots available in the lab as well. You can also pick one of those. The introduction today is mainly about the theory of mobile robotics. If you check the Nextcloud, there's also a video about how to set up this Jetson chatbot platform and how to use it. One of the past students recorded a video. I think I already told you before, it's a video, but if you play it in the browser, there's some issue with Nextcloud, then you only hear the audio, so just download the video and watch it locally, then it works. And that's more for the technical setup. And today we'll talk a little bit about the theory of all of this and see how it works. For the chatbot platform, there's also a GitHub repository with code and lots of explanations. And we bought the kit from Waveshare, but there are obviously many other vendors that offer a package like this with a somewhat related robot. When you think about mobile robots, I think they are overall something very interesting, because it's not just a static robot that stands somewhere, but a mobile robot can interact with its environment. So it needs actuators for moving, and it needs sensors for understanding its environment. There may be more actuators for manipulating the environment, but it's something that doesn't matter for the robots we're using here so far. So we need sensors to understand the environment, and we need to be able to move. So we need actuators for moving. And what we also don't like are power cables to the robot. So we actually need some battery, which is far better than if our robots have a cable. We also need some computing power on board, at least a CPU, but because we want to do a robot vision project, we are interested in cameras, for example, and things our robot could do is eventually it could explore its environment and try to avoid obstacles. It could do localizations or figure out where it is on a given map. We could also try to learn a map from our unknown environment, and we could also plan a path throughout this environment. And given the concrete task that we want to work on, our robot obviously would need some more features on top of that, like a cleaning robot or something. But that depends concretely on the exact use case. But what we've seen here are the minimum features our robot actually needs. Then we can use mobile robots for many different tasks. I've already mentioned cleaning robots, that's one thing, but there are a whole number of field robots. We could use robots for exploration, search and rescue, mining or heavy transport, container handling. We could be thinking about all sorts of military applications, and the robot that I've just mentioned, the cleaning robot, would fall into the category of service robots. And there are obviously many more service robots you could think about, like lawn mowing, laundry, medical robots, transport robots, and in entertainment, we could be thinking about robots like Lego Mindstorms and so forth. And there's far more than just robots that move on the 2D plane. We could also be thinking about drones, for example. And obviously, you're most welcome to use a drone as well for your project if you wish. You're not constrained to these robots we are providing you. If you have other robots at hand that have a camera, you're most welcome to use them. Now, our mobile robots, they're not just fixed somewhere, but they are actually moving. So we need to be thinking about autonomy. What is really good is obviously the goal of building a fully autonomous robot that just does the tasks on its own. The very difference could be a teleoperation. Don't know if you remember this TV series Robot Wars from the past, which looked like robots combating each other, but in fact those were just teleoperated robots. They didn't work autonomously. And then you could have something in between that are semi-autonomous robots, for example, like a Mars rover, which can do some tasks autonomously, but for others needs guidance. And when we want to do our calculations on the robot, so on the edge, we actually need some sort of CPUs on it, whether specialized or general, at least for the basic processing. And then if we want our robot to do more, for example, vision, we would need, for example, GPUs, because GPUs are very helpful for convolutional neural networks, vision transformers, and this kind of stuff. But there's other hardware you could be thinking about as well to put on your robot, like an FPGA, so a field programmable gate array for specialized tasks. And the platform we have chosen is we have a GPU, not too complex, but at least a GPU available that we can use for inference on the robot. Training is something we would probably be doing on a computer or in the cloud, and then move the trained model on that mobile robot. And we use the GPUs that we have available largely for inference in our setting, because if we put very big GPUs on the robot that can also do efficient training, we need a much bigger robot, we would need much more energy, and probably would become far more expensive. So with our setting, we can do inference quite well, and training you would do on your computer, on a server, or in the cloud, or wherever. Then there is also some interesting history about the foundation of mobile robotics. In the US, there is an agency called DARPA, and DARPA is tied to the US Department of Defense, and DARPA's goal is to recognize trends early and invest in those early, always with the goal of utilizing this for military purposes at some point. And they organized the Grand Challenge about 20 years ago. There was one in around 2004, and they had the goal that there are cars autonomously driving a course, and they wanted and they hoped that a few teams would actually make it. But that DARPA Grand Challenge in around 2004 or 2003, whenever it was a failure. None of the cars made it. And then in 2005, actually, a few cars completed a much longer desert course. In fact, the Stanford team the won that challenge in 2005, and they completed a 175-mile desert course autonomously in just a little bit under 7 hours. And this actually led to a huge boom or hype around autonomous driving, because it was shown that it's actually possible, even in a desert course that is more than 200 kilometers long. And the Stanford team was led by Sebastian Thrun, who then went on starting portals like Udacity and worked on lots of other stuff in addition to his work at Stanford. And since then, I think we've seen a lot of progress in autonomous driving, and a lot of that goes back to what happened in 2005 at the DARPA Grand Challenge. And there are obviously other interesting mobile robots that are now available. For example, autonomous cleaning robots, and they're also becoming better and better, and they actually include a lot of AI nowadays for mapping and localization, and combining this into an approach that is called SLAM, which is simultaneous localization and mapping. But I'll say more about SLAM later. Now, before we come to fully autonomous robots and AI and SLAM, we need to first go to the foundations of robot motion and describe how a robot can actually move in a 2D plane, 3D plane. And what we want is, we want speed. So we don't want a robot to take forever, but we also want a precision of positioning, so that we actually can reliably get to a position and we could repeat this without moving off further and further. And we want this flexibility and robustness in different conditions, for example, when there's rain or snow, or depending on the surface. And ideally, we want to do all of this at low power, so we can actually reach far with our battery. At least these are the ideal conditions we want to reach. It's not that easy in practice, I know this, but at least these are some of the goals we aim for. And that's why we also largely would do inference on the mobile robot, and not too much training while running, because if we did that on the edge, probably we would quickly run out of power. So maybe for more complex tasks, we would send the data through our network to the cloud or a server or some other computer where we can run those computations, and then send the trained model back or the updated model on the edge device, like the mobile robot. And the first part today will be about that we describe motions of a mobile robot. We will stick for now with a 2D world. So it's a mobile robot like the ones I have shown you before, but we can obviously extend this framework to a 3D world where we would have, for example, a drone flying around, but we'll stick with 2 coordinates for now. And the robots we're using in this course, they have essentially 2 wheels, or at least 2 wheels, and one on the left side and one on the right side. You can have more wheels if you want, for example, for stabilization, but the platform we are providing you, we have exactly 2 wheels for moving and a very simple one for stabilization, so it doesn't fall and keeps driving in a stable way. And if we have these 2 velocities, so we have a velocity of the left wheel and the right wheel, if they are exactly the same, the robot would actually move forward And if they are just at opposite speeds, but equal in terms of the absolute value, this would allow us to move the robot on the spot. These are the two extremes, so either move forward or just turn on the spot. And when we try to visualize this, we can actually come up with much more combinations of these two speeds and actually describe how the robot moves in a circular arc. Something like this. So we have our mobile robot, and we have a couple of variables now that we need to bear in mind. And I will also visualize this later on the iPad at some point, once we come to describing how the robot moves. And what we have is, we assume now we have these two speeds, velocity of left and the velocity of right. So left wheel and right wheel. And if they are exactly the same, the robot moves a straight line. If they're just the opposite, so one negative, the other one positive, we would just turn on the spot. But if one velocity is faster than the other, then the robot moves on this circular arc. And the variable W describes the width between the two wheels. And if we drive a circular arc, our circle has a radius. And if we drive, we have a certain change of angle that we have moved on the circle. And this is described by delta theta. So how far we have moved on the circle in terms of the angle. And bear in mind these three variables. If you, well, I'll just change to the iPad at this point, and then it's probably easier to visualize. So just give me a second to switch to the iPad. So we can describe the robot motion, and I'm just copying the figure from before to make it more understandable. So this is our delta theta, the angle. We have our radius, which is r. And we have here the two wheels of our robot. And the distance between the two wheels is called W. And the robot would move, and then we would have the wheels somewhere up here. So this was just the figure from before. And we can also, now we wonder if we have these two velocities. So we have a velocity of the left one, the left wheel, and the velocity of the right wheel. We can actually derive how to calculate the delta theta and the radius. What we need to bear in mind is important for the left wheel. We want to calculate its distance that has moved, and the distance of the left wheel, so right is here, is VL times delta t, because a certain amount of time has passed where the left wheel drives at velocity VL. And for the right wheel, this would be VR times delta t. So this is the distance that we have moved. And we can also describe the radius of the arc. The radius of the arc for the left wheel is r minus half of the width, because we would have this point here. So we have r, which would go up to here, minus half of the width. So we have this position here, And then from there, this would be the radius of the arc. And for the right wheel, we take this center. Let's say, well, it's r plus half the width for this remaining distance. So with these two equations, we can describe the distance of the distance moved and the radius of the arc. And it turns out that you can also, from there, describe the radius of the robot, as well as the change of angle. This is shown in detail in the slides, so I don't need to describe this here because it's a bit of a longer equation. But I'll show you this now in the slides. So we had just derived the distance moved and the radius of the two arcs. And in fact, from there, you can say, well, the wheel arcs subtend to the same angle, obviously. And you can say, well, it's our distance divided by the arc, divided by the radius. That's the angle. And this is the same for the left and right wheel. For the left wheel, we have VL, and our radius was r minus half the width. And for the right wheel, it's VR divided by r plus half of the width. And then, or plus half of the width. And then you can just reformulate these terms, and eventually you will get equations to calculate the radius of the robot, as well as or the radius of the arc, as well as your delta theta. It's just by rearranging these terms, and you will come to these two terms in case you need them. And that describes the robot, because we could derive this from the left and right wheel. Then we need a concept that we call open and closed loop control. I'm not sure if you have come across a term like this. So I'm asking you, has any one of you ever come across the concept of closed loop control or a PID controller? If you have ever heard about this concept, maybe a thumbs up. If you have never heard about such concepts, maybe a thumbs down. And probably most of you have not come across this. However, some of you have heard it, so that's good. Now, I'll start with an open loop motor control, because now we need to look a little bit more into our motors, and we can see how to move the robot. And the concept of open and closed control can be applied to far more than just these motors. It can be applied to many other dynamic systems. And for our open loop motor control, you need to imagine I have my motor and I put in a voltage. And what I want to get out is a value Y, and Y is some value of how quickly the motor would move. And I put in a voltage, and I want, for example, this to drive at 1 meter per second. Sounds good, but it doesn't work that easy, in fact, because in reality, we need, for something like this to work well, a closed loop motor control. Because if I put in some voltage, I will probably not just get exactly the velocity I wanted. Because there can be all sorts of issues why it doesn't work that way. For example, there's some more friction on the floor, or maybe some minor some dirt on the road, or maybe uphill, and then I would need more velocity, more voltage to actually get my velocity. So I somehow need to be able to check the difference of what I'm getting compared to what I actually wanted to achieve. And for this, I need the concept of closed loop motor control. And it's an extension of the previous concept, our open loop motor control. And what I have here is at the end, the open one, that's the concept we just saw, and I'm getting out my velocity, for example, or some other value, because you can apply this to far more than just motor control. And I'm putting in my reference, my desired output, and then I'm checking, because this is a closed loop, as you can see, what I'm getting out is my current value y, and I'll check if there is a difference between y and the actual value I wanted to get. So for example, for a closed loop motor control, I want the motor to run at 1 meter per second. I'm putting in a certain voltage, but right now it's only running at 80 centimeters per second, for example, not 1 meter per second. So I have a difference, and I can calculate the difference here because I have my reference value and my actual value I have right now. And for this difference, I have an error, and I put that error in my controller. And for example, if I need to speed up, the controller would then, as a consequence, put a higher voltage into our module from before, our open loop motor control. And then the motor would speed up and maybe reach its speed at some point. If I put too much velocity on it, I would overshoot and be at more than 1 meter per second. Again, then I have a different difference. And then the controller would maybe, in consequence, put a smaller voltage into the open loop motor control. And at some point, this will converge. Initially, it's maybe too low. I put on more voltage, then it's maybe too high. And then my goal is to actually converge. That's the idea of a closed loop motor control. And this concept can be used for so many other things. For example, you have a drone and you want that drone to stabilize at, say, 2 meters above ground. Initially, your drone is maybe at 1 meter above ground, and the drone will accelerate and try to race, but then it overshoots and it maybe stops at 2.5 meters, which is too high. And then it will go down a little bit. Maybe it goes just down very, very slowly or too fast. And then it's at 1.8 meters per second, goes up a little bit again, and it tries to stabilize. So you can also use closed loop motor control in a car, for example, as an end user for cruise control. So you want your car to run at 150 kilometers per hour. And for example, if you drive uphill, the car will automatically accelerate just in order to keep your desired speed. And this concept of closed loop motor control is something that comes from the field of control, and it's a different approach to solving certain problems than what we do in machine learning. However, if you talk to people from signal processing, they may aim to combine machine learning and such classic control techniques. That's also what some people do. And I think for the kind of problems I have described so far, a closed loop motor control or a closed loop control works very well. And we can use it, for example, for motor control, but for many other things as well. And there are all sorts of closed loop control techniques. And one that is a very famous one is the PID control. And PID stands for proportional integral differential control. And in fact, for our controller, we now have 3 components. We have a proportional part, we have an integral part, and a differential part. And I'll explain you this now step by step, and you see what it's useful for. So for our controller, we have the proportional part, and the goal is with the proportional part to reduce the error. We can have a factor Kp that allows us to customize of how much we want to take this proportional part into account. But then we have made previous corrections because it's a closed loop system. So in the last loops, we had done corrections. And maybe if I just use the proportional one, then I'm maybe over and undershooting, as I explained before with the drone. That first is too low, but then too high, then too low again, and actually converges maybe slowly. So in addition to the current error that I want to take into account, maybe I want to take into account the last few errors. With this integral, I say, well, t0 to t, this would say I take all the past errors into account and I integrate them. If it's in case it's continuous, if it's discrete, I can also just imagine that I do this with a sum sign in order to sum up the past errors. And again, maybe I don't want to take this fully into account. Again, I need a certain constant in order to reduce the impact of the integral part. Sometimes you would not take into account all past errors, but maybe the last k many errors. Maybe you would say in the last 10 iterations of the system or the last 100, whatever, depending on your use case. Maybe not from t0 up to the current time, but just the last few ones. And then you have the third part in which you look at how the error has just changed from the last iteration of the loop to now. So we're taking the derivative of the error, and this is just a change of error. And that one you would also take into account with a certain factor. And then you have these three components: proportional, integral, and differential. And you can customize it because you need to find these constants for Kp, Ki, and Kd. If one of these constants is zero, that part would just fall off. So if we just kick out the differential part, this would be a Pi controller, so a proportional integral controller. If you only take the proportional one and the differential one, this would be a PD controller. So you can imagine all these combinations. And there are also various strategies of how to find Kp, Ki, and D. Something that is like a heuristic rule that you sometimes can't come across in the literature is something you set Ki and Kd to 0, and then you slowly increase Kd, so the constant for the differential part, until the system starts oscillating. We don't like oscillating this too much, so only when it starts to oscillate we stop. And we call this gain Ku, so up to where we could move Kd so that the system starts just oscillating. And then there are certain rules of how we could calculate Kp and Ki. This is something, feel free to try out once you set up your own PID controller. And now you're wondering, what is this useful for? I mentioned a few use cases, like, for example, cruise control. We just want to keep the same speed, and based on how, based on maybe if there's a certain angle that we're driving up or down, or friction on the ground, we may have to put more or less voltage in. So this is somewhere where we could be using a PID control, or I mentioned the drone if you want to stabilize it at a certain height. I have also used this kind of or this methodology, for example, to calibrate robots. If we have our left and right motors, then they, in an ideal world, these two motors would be just behaving exactly the same, but in fact they are not, because these two motors, they will always be behaving slightly differently. So if you put the 1 volt or 1 voltage on the left and the same voltage on the right motor, they may run at slightly different speeds, and you don't want that because you want them to drive straight. So with a PID control, you could actually solve this and be able to use these two motors that behave slightly differently, but make sure they run at the same velocity. This is what I have, for example, used this for. It's maybe something that you come across your robot as well, that maybe one wheel or one motor moves a little bit faster than the other one. And if you want to calibrate this and make sure they behave the same, you could be using a PID control, for example. Then we can now start describing some motions of our robot on the 2D plane. And from now on, we will be describing our robot as a vector. And the vector is called x. And our robot has in the 2D plane an x coordinate and a y coordinate plus a certain angle. So where the robot is currently looking at. Initially, we say a robot is starting in the beginning, for example, in the center of the coordinate frame. So x and y is 0. And we also need to define what an angle of 0 means. And typically, this could, or it means a certain direction where the robot is looking at. And I will again describe this now as a figure on the iPad to show you that. So we have our robot coordinates. And we have our coordinate frame. So we have our center here. It's the center, 0, 0. And we have our x and y axis. We have the x-axis, and we call this x. Yeah, we call it x and y for now. And then we have our robot. It starts initially in the center, and at some point, the robot has moved to, for example, here. So this is now our robot, and our robot looks at in a certain direction. So we can say this is our robot, and it's looking, try it better. This is, for example, the robot, aiming that the red dot should be somewhat the center, and the robot is looking in this direction. And then a typical convention would be that this angle between where the robot is looking and the x-axis, this is called theta, which is our angle. So down here, the robot was in 0, 0, 0, because the robot maybe initially looked in this direction, and then the robot has moved to up here. And we could say this is, for example, 5 and 3. And now we can describe the robot as at 5 and 3, and it would look here, for example, at 30 degrees. This would be one way how we can describe this. Ideally, you don't use degrees, but radians. So between what you would typically say is that for this coordinate, we only put in the first example here 30 degrees because it's easier to imagine. But typically, we would say that our angle theta is less than or equal to pi and greater than minus pi, because it has 360 degrees. And we don't say it's between 0 and 2 pi, but rather between minus pi and plus pi. And the convention is that here we put a less than sign and here a less than or equal to sign. And when your robot rotates, always make sure later that its angle stays in this valid interval, and that not suddenly, if you keep rotating and rotating, that your robot has like a 30 pi angle or something. That's what we don't want. Now, our robot will also move, and I've visualized this here already with a concrete example. And it's just a made-up example for now, but I will describe this now in a more formal way. When our robot moves, And from now on, we assume it's a straight line movement. Then we will update our vector, and the new x, the new y, and the new angle will be calculated the following. One thing is important. If I do a straight movement, so my robot is looking in a certain direction and I'm moving it, then the angle doesn't change, because it's just a straight movement, so the angle stays as it was before. And for x and y, I add something on top. Concretely for x, I add on top d times the cosine of theta, and for y, it's d times sine theta. And d is just the distance. So the distance before would have been this one here, assuming the robot, first of all, changed its direction and then drove from here to there. And then this would be the distance, and you would update x by adding d times the cosine of theta, and y you would update by adding on top d times the sine of theta. But this is just fundamental geometry that you're familiar with, and my angle theta does not change. This is the straight line motion. I'll leave some space here because later we will see that this becomes a little bit more complex in reality. So I'm leaving some space, and we can also describe a rotation. And the rotation would only affect our angle, because if we rotate, then our x nu and y nu, they don't change because x and y just stay. But what changes is the angle in a rotation, and we would have our theta, which I also just keep in black, and we add something on top, which is just our alpha. So a rotation would be that it rotates further, and then the robot would look here, and then this would be theta plus our alpha, and this alpha would be just this extra rotation from here. This is all well formatted also in the slides, which looks nicer than the handwriting here. But with this, we can easily describe our fundamental operations, a straight line motion and a rotation. Later, we will see that in practice, it isn't that easy because there's uncertainty, but the uncertainty will only come in a few minutes. This is what we just discussed. I've mentioned the angle, and I've drawn something like this, and I've just shown you the straight line motion and a rotation around an angle. It turns out if you don't want a straight motion, but you're using different velocities of the two wheels in order to move, so you're doing a circular movement, you can also describe this, and you can write your x nu, y nu as something like this. It takes a little bit of time to derive. We're not doing this here because just in order to keep our movement simple, we will just use for now straight line motions and rotation. So if I want to move somewhere, I first rotate in that direction and then I move there. But you can do circular motions as well. Before, I have shown you from the velocity of the left and the right wheel how we can calculate delta theta. We have also seen how to calculate r of that circle, which is shown here because we have r of our circle and we have our change of angle. We calculate this from the variables we have seen before, and like this, you can calculate your new x and your new y and your change of angle. Feel free to implement this if you want to do it. It just takes a little bit of more time to derive. But if you want to implement this in your project, you can just implement these equations You don't need to derive them on your own. And if you use a more high-level library, this kind of stuff is anyway already available for you in these libraries. Now, lots of text here, and I'll probably go back just on the whiteboard to show what all of this text means. And the text is for you and your own revision. So, what we need is position-based path planning. So we have our coordinate frame. And we have our robot right now here looking in this direction. And we want our robot to go there. So this is position 1, and this is position 2. And we can pose it like this. And right now, our robot is, I'm writing it here, X and Y and theta. And we want the robot to move here. So first, the robot needs to rotate. And rotating is a little bit more complex to express mathematically, but I'll show you this later. For now, we say the robot first rotates, then the robot looks in this direction, and then it drives to this waypoint. And in order to describe this, we can say our point 1 has an X and Y coordinate, which we call just X and Y. This is where our robot is. And the position 2 we'll call now we just use the same convention as in the slides, which we call the waypoint. So we want to go from the current location P1 to P2, which is that waypoint. And what we need to calculate is we take the X coordinate of the waypoint and subtract our current X. And for our Y coordinate, we take the Y coordinate of the waypoint and subtract our current Y. We need to calculate the angle. The angle is something I will show you very soon how to calculate it. And once we have calculated this vector here, we can also call this vector, we can give this new names, and we can say, well, this is dx and dy. So how much we have to change x and y, plus we calculate this angle. And then we need a certain distance. So how far we need to drive. And this distance can also be calculated just with basic geometry. So the distance is just the square root of dx squared plus dy squared. For this example, it's obviously super easy to do this because we're just moving up in y. We don't change x, but obviously there could be a different waypoint, like here, waypoint new, and we would have to drive here. And then we have a change in x and y, and we're not just changing the y value like in the green example. The only tricky part is how can I calculate this angle efficiently? And for this, we need a little bit more maths, which I'll show you in the slides again. We have just seen this, our change of x and y to get to our waypoint. And in order to calculate our angle alpha, so how much the robot needs to rotate first before we can drive the distance, what we could use is the inverse tan function with an argument value of dy divided by dx. again, basic geometry, how to calculate this rotation we need to take. But it isn't that easy, because it could happen that you are rotating more than 180 degrees. Imagine you actually have your current position and the waypoint, and you would just have to rotate a little bit to the right. But so far, how we describe the rotations, we always said rotate to the left, and maybe you only need to rotate, say, 60 degrees to the right. But with our approach so far, we would be rotating 300 degrees to the left. So this takes longer. It also takes more energy. So we don't want unnecessarily complex rotations. Rather, we want to rotate those 60 degrees to the right then, rather than 300 degrees to the left. And because we need to take care of this, we can wonder about in which quadrant we are and how to use the tan or the inverse tan function in order to do this. Or you simply use the tan2 function where you pass the argument dy and dx. We have seen the tan2 function a few weeks ago in this course in one of the feature detectors. And I mentioned we would need it again at some point, and this is today. The tan2 function is implemented in typical math libraries, also in Python, so you can simply use it and you pass the arguments dy and dx, not just a fraction that you calculated, and the tan2 function will just return you the right angle. And in this case, it would just return you the smaller angle, and you would then rather rotate to the right than a long angle to the left. Feel free to read the documentation of the tan2 function and see how it works, or you simply just bear with me and use it and try it out once you have your robot. This is something we had also just discussed, the distance that we need to move, dx squared plus dy squared, and we take the square root. Now we have described initial movements of our robots. Now our robot can move on a 2D plane. What we have from initially is the velocity of the left wheel or the left motor and the right wheel. And from there, we can describe everything. We can describe how to rotate our robot, how to move it straight. We even saw this one case, how to move it in a circular way, but we won't be doing that too much now. And we can rotate it and then move it in a certain distance and make it there. In practice, this doesn't fully work because there is uncertainty. Uncertainty is something we'll discuss later today. But there are, in addition to movements, a few things we also need, which are sensors. Because so far, our robot is just blind. It can only move and it doesn't know anything about its environment. So we need sensors. We as humans, we have sensors, for example, our eyes. We have other sensors like ears and so forth. And so our robot also needs sensors. For example, there are sensors that we can classify sensors into two categories, like proprioceptive and outward looking. The first category, proprioceptive, would just mean something like self-sensing. Such a robot would not interact, or such sensors would not interact with the environment. Rather, such sensors would just give us a sense of the robot's internal state and motion. For example, such sensors could be used for some error analysis, or, for example, a gyro in order to report the current rate of rotation, because this has nothing to do with measuring the environment. But you could also get maybe some insights about the wheel odometry and so forth. But most sensors we're actually interested in, they are outward-looking sensors. And outward-looking sensors, they will actually depend on both the robot X as well as the world around it, which we call Y. Because our previous sensors, the self-sensing ones, there the measurement only depends on the robot, but not on the environment. And here it depends for the outward-looking sensors also on the environment. And I'll look with you now at a couple of sensors which fall into this category. The applications of outward-looking sensors could be, for example, you could localize where the robot is in a certain map. You could try to recognize places and objects. You could try to build a map from what you're observing, and so forth. So it allows the robot to actually understand its environment. And there are simple sensors of that sort, for example, touch sensors. These touch sensors, they would just report a no or off if they didn't collide with anything, or an on if there is a collision. So it's not a camera or anything advanced like this. It's just in order to report if the robot bumped in something or not. What you see here are photos from Lego Mindstorms robots. The beauty of these Lego Mindstorm robots is actually you can easily build your own robot, and you have all sorts of hardware available. The software from Lego Mindstorms isn't that great, so maybe for software you would be using something different with a Raspberry Pi or something, and also use a different CPU. So for example, a Raspberry Pi or something else. But these sensors, they are actually pretty useful from Lego Mindstorms. And with Lego, you can just build your own robot as you wish, and you can customize it, and you can use the sensors. So overall, this is something quite helpful when you're starting. When you're colliding with something, then you may need a strategy of how to keep moving. Maybe you would just reverse. Maybe it's a moving object that is lightweight. Maybe you could just push it away. So that, again, depends on your use case. There are other sensors, like a light sensor. It would indicate, this one could be used, for example, to follow a light source, and you want to increase the intensity. And if such a light sensor allows you to measure intensity of light, maybe you just want to move to a location where this intensity goes up. There are more advanced sensors like a sonar. So a sonar emits an ultrasonic pulse and measures the echoes. And with such sonar sensors, you can, for example, measure distance to objects. And this is used both above ground as well as underground, for example, underwater, where it's generally difficult to work with cameras. That's where sonar sensors could also be interesting. And sonar sensors, they are quite cheap, yet they allow you to measure distance. For some robots that you find in our lab, you may have sonar sensors available. For this chatbot platform from before, we don't have sonar sensors, but I've seen students in the last years, they got their own sonar sensors and still added them on top of the chatbot. But in this computer vision course, we are interested in cameras. And this robot kit we gave to you actually has a camera. And cameras are really good because there's a huge link to us as humans, or we can see, so there's a huge link to biology. And with these cameras, you can see the environment, and you get much more insights than just with a sonar or with a light source. However, there are certain challenges with cameras. Processing the images or videos that the camera returns is computationally expensive. You need a lot of power, probably, so your battery will be empty quicker. But nowadays, cameras are quite cheap. That's the advantage, because now you can buy cameras for general purpose, low-cost robotics. If you look at how much our chatbot kit costs, it's extremely cheap, actually. When we bought them a few years ago, we just paid maybe 200 euros per robot, which included a camera. We needed to buy the GPU, which was maybe another 100 euros or dollars. Nowadays, it's even cheaper. So mobile robotics using cameras has become cheap, yet processing images or videos is computationally expensive. So we need a GPU, and we need enough battery power. I've said before that these motions that we have described with our vectors x is how it would work in an ideal world. In the real world, it is not that easy because dealing with real robots or real mobile robots is messy. And we have lots of uncertainty. We have uncertainty in motions, because if we want our robot to move 1 meter, it will not precisely move 1 meter. Measurements also come with noise. And we now need the tools in order to reflect uncertainty in our models. And for this, I will again switch back to my slides. So we're coming to this one here. And we said that in an ideal world, if we move our robot by a straight line, we just add d times cosine of theta on it. But the robot will not move precisely by distance d. So in a real world setting, this equation would become a little bit more complex. So I'm here now writing real world, adding uncertainty. This vector would actually look something like just writing down the parts from before. And you will see it will soon become a little bit more complex. Because now in the real world, this will not move precisely by distance d. Rather, there is some error on top of it, which is positive or negative. So we're saying d plus e times this cosine or sine. And even if I move a straight line or aim to move a straight line, my robot will not precisely move a straight line. Rather, the angle will also change. So I say this is now theta plus f, because the angle will slightly change because maybe one wheel drives a little bit faster than the other, or there's some extra friction on the ground or some dirt or something why it doesn't work the way I wanted it to work. So the angle will slightly change. And for our rotation, there will also be some real world change because we have x and y, and we have our theta plus alpha, but we still have some error on top, which I call g, because if I want to move it by alpha, it will not, or rotate by alpha, it will not fully rotate by alpha. Rather, there's some error, positive or negative, so it will either rotate a little bit too much or not enough. So we need to reflect this uncertainty in our models. And now you wonder, how big are these errors, E, F, and G? When we calibrate a robot, we want to keep them to an absolute minimum. And for calibration, before I've already mentioned, for example, PID control, which is one approach. And then maybe depending on the environment where you put your robot, this will again vary. Maybe on certain floors or on a certain surface, it will move better than on a different one. How to measure this exactly is something we will see, but it's certainly something you need to bear in mind, that there's always some error in the distance as well as in the rotation. And E, F, and G are our error terms or noise terms. A good assumption that you would typically take is that you would describe these errors, or you would say these errors come from a Gaussian distribution. And ideally a very thin one, but if you make it too thin, maybe again, it will not give you adequate results. So you need to model the right Gaussian distribution depending on your robot and the setting. But all of this will become more relevant now, and I'll show you a little bit more about how you can quantify uncertainty. What we need to do is, or we start with an example, it's something like this. Imagine our robot starts in a location, like here at 0, 0. And the robot now has the task of moving straight, so along the x-axis for 10 meters. And then another 10 meters, and another 10 meters, and so forth. And when we do this, the robot will not precisely end up over here in the center. Rather, the robot will be a little bit off to the left or right or front or back. It will be scattered around this center here. And what I've visualized here in my plot is I've simply found values for our noise terms E, F, and G that we have just seen. And I have created multiple particles for this plot, and each particle is moved by 10, by 10, by 10, and by 10. But there's always some error on top of the movements for the E here. And these errors are drawn from a Gaussian distribution. And we will finally see the more we move all these particles, the more they will deviate, because then we will feel the noise more and more. What we see here is this small black circle. The small black circle is, in our case, just a center. So the center of all these particles, that means in average, we are where we want it. And we still have this arrow here, which is the direction. And in fact, this direction is the average direction of all the particles. So far, this has not really changed. Now, the next task is rotate all of this by 90 degrees. So the robots will point up here, or the particles, and then again, move them by 10, by 10, by 10, and by 10 meters. And then we see, after this rotation, and we move them forward, they spread more and more out. We still have the center more or less where we wanted it to be. And in average, these particles still point to our actual location. But if we zoom in, we can see that for each particle, we also have this direction. So some particles point a little bit more off than others. Okay. But the average is still okay. And then I want this to rotate. I want these particles again to rotate by 90 degrees and then move them. And I see they start spreading out more and more. And then again, I rotate them and move them. And I will see that by moving 10 meters, 10 meters and 10 meters, so 40 meters, then rotating, move by 40 meters and so forth, most of my particles, they don't end up in the origin where they actually come from. We see they're actually spread around. And we can see that this is, well, somewhat like normal distribution, normal distributed, that probably most points or most particles are very close to the origin, and some are further spread out. So this is one visualization of how this noise in movements could actually impact the location of our robot. And we later need to see how we can correct for this. Ideally, you do good calibration, that they don't spread out much, but there can still be some issues with the surface, whatever, that leads to these effects. But, and here you actually see the beauty of this being a vector plot. So one piece of advice is, if you ever generate plots with a library like matplotlib or something like this in Python or with other libraries, always try to export these figures as vector graphics, not as pixel graphics, because if you have a vector graphic, you can keep zooming in and zooming in. And if you have a LaTeX document, for example, so you are writing a thesis or a report in LaTeX, you can import these plots as a vector graphic, and then it allows you that you can keep zooming in and zooming out. And with a pixel image, this wouldn't be possible to this quality. And also printing a vector graphics typically looks much better than a pixel graphic. So this is my piece of advice. If you write a thesis or report in your studies and you have plots that you generated, always generate them as a vector graphics and then import it as a vector graphics, for example, in your LaTeX source. We see that this robot, one could argue, is maybe still okay calibrated. Obviously, there's some variation, but now we could have a very poorly calibrated robot, and we see that these particles spread out a lot very quickly. You see, we keep moving, and already here, after 40 meters, they have spread out so much, which are these orange ones. And if I rotate them and then move them, they spread out even more. And eventually, like green and blue means more steps, but we see now actually after rotating them up here again, they totally spread out. So this is really a poorly calibrated robot. And this one here is relatively well calibrated or okay calibrated compared to this robot. There is a whole theory about how to calibrate your robot. Ideally, you would model these errors through some distribution, and you don't want systematic errors. So a systematic error removed means that these errors have a zero mean. That's important. Otherwise, if you have a systematic error, that means the errors don't have a zero mean. You could have more, maybe some bias or systematic error towards the right. If you have something like this, that your errors, the movement errors, don't add up to, or their mean is not zero, but you have a mean that is somehow positive or negative, then you have a systematic error, and this could mean that your robot shifts to the left or right, for example. So that means maybe you need a better closed loop control for the motor, so that you actually have the two velocities being the same and that the robot doesn't drift to the left or right. And this robot here maybe could be calibrated better, obviously, but it has no systematic error because we see these means, which are these black circles. They are exactly where they are supposed to be. So this one here has no systematic errors. This one is so bad, it's hard to quantify, but it definitely has systematic errors. We can model these errors typically with a Gaussian distribution, and the distribution of the errors will grow as the robot moves around in the space. So if you keep moving the robot over and over, obviously you will have more uncertainty. So at some point, you also need to localize the robot, that the robot finds out where it is in a map. And this is something we'll be discussing now, where we're slowly making our way there to see a framework that allows the robot to localize in a known map. And there's a lot of theory again in here. I'm just saying the essence, and there's a lot of text in the slides for further revision, but I'm just providing the essence, and some of these slides are further reading if you want. We will go directly to a practical example and see how we can actually localize. And these few slides before, I'll say this just orally when we need it, and feel free to read them for further revision. This is now a map that we have. And we have a robot right now here that is in a certain location and has a certain angle. And it's a known map. So it's a known room or a factory, wherever, where we put in the robot. And the robot knows this map and it's unable to leave the map. Now, as the robot keeps moving around in this map, it will obviously have uncertainty in its motion. So if we first want to move the robot to the right and up and then back and up here and down, the robot will internally keep its state, so it's X, Y, and it's theta, But at some point, this is just off from reality, because if you want the robot to move over here, it will maybe move somewhere around there, then up and rotate. So where the robot is in the real world will more and more diverge from where the robot thinks it is, just because the robot thinks it really moved 10 meters, but maybe only moved 9.8 meters. It didn't fully rotate as wished. So at some point, we need a check with reality. And this is localization, that the robot determines where it is actually in the map by doing measurements. Because the challenge is every robot action is uncertain. Now we say we want to do some sensor measurements that a robot could somehow measure where it is in a map. Again, sensor measures are uncertain. And in fact, we are doing a state estimation. We're now looking at a filter method that we call a particle filter. You've learned about the Kalman filter last week, and today we are looking at the particle filter, which is a different state estimator, specifically helpful for localization in maps. Well, later, if you want, we can also contrast it a bit to a Kalman filter, but it just serves a different purpose. And what our robot now will do with a particle filter is we will move the robot around, it will take certain actions, it will do measurements, and we actually want to include these measurements into our robot state and do a state estimation, assuming that the robot actions are uncertain and the sensor measurements are uncertain. What we need for this is Bayes' rule. You all should be familiar with Bayes' rule by now. We looked at it last week, we revised it. We needed it a lot for the Kalman filter, because what we want to calculate is P of X given Z. So what's our state X given the sensor measurement, which we also call the posterior. And we can calculate this by saying P of Z given X, so the probability of the measurement given the state estimate, times the probability of the state estimate, where this one here is called the prior, this one here is called the likelihood, and we need a normalizer. If we drop the normalizer, we just need some alpha as a normalizer constant, something quite common that we have also seen last week with the Kalman filter. And we will use this Bayes rule now to actually update our state estimate. So what we know about the robot state given measurements from the sensors. And again, just a quick revision about probability distributions, but you're all familiar with this and also with the Gaussian function. We will now discuss step by step how the particle filter works. We will also look at a video in a second and see how the particle filter works. And the particle filter is something that is also called Monte Carlo localization. What it does is our robot will have its state estimate. And this state estimate is obviously something we need to filter from the actions we take and sensor measurements. And sensor measurements could be, for example, distance. So how far the robot is away from the nearest object. It doesn't know which object. For now, we just assume we have like a sonar, and the sonar just measures how far the robot is away. But our robot also knows that these measurements are uncertain, and when the robot moves, those movements are uncertain. So what we do is, we will now have in our software so-called particles, maybe like 100 or 1,000, whatever, that represent our robot. And to all these particles, we will apply the action we're taking, like a rotation or movement, and we add these error terms. And these error terms come from a probability distribution, for example, a Gaussian distribution. So some of these particles will have more errors than others. But then we take a measurement, and the measurement is the distance to the nearest object. And then we factor this into each of the particles. And for some particles, that measurement makes a lot of sense. While for other particles, that measurement doesn't make much sense because maybe the particle is just too off or it looks in a totally different direction. And then we only want to keep in the next iteration the particles that are actually most likely. And we want to delete the unlikely ones, and the most likely particles we're just going to copy. So what we are doing is we're going to do some kind of resampling because we want to keep the likely ones and remove the unlikely ones. And then from these particles that we have, we can estimate our state. And then we take the next action, like the next movement, and apply these errors again to our particles. And then again, do a measurement, factor this in, and only keep the most likely particles. And there's a video for this, which you can find on YouTube. The video is from Coursera, because Coursera offers a course. Sorry, it's not Coursera. I was wrong. It's Udacity, just a competitor. My apologies. So it's obviously from Udacity, the competitor of Coursera. And on Udacity, there's this course, Particle Filters AI for Robotics. And there's a video that shows how the particle filter works. I will discuss this video with you now. I'm unable to put this here in the recording, so I will just briefly stop the recording for a few minutes because of copyrights with the video. But you see the URL here, and you can play the video on your own. But only for the ones who are joining live, only those can hear the explanation of what's happening in the video. So I'm quickly stopping the recording, and welcome back to the recording. Feel free to watch the Udacity video on your own, and you'll hear an explanation in there as well from the author. I've just discussed it here with the students, and I'll discuss now with you the framework of how the particle filter works. So we have a certain number of particles, for example, 100 particles. And for each particle, we have our robots, or the state of the particle, location X and Y, and an angle. And then for each particle, we also have a weight of how likely that particle is. And then we have, for example, 100 particles. So we have a set of all of our particles of the particle filter. And it's important that these weights, they need to add up to 1. That's a condition, but if our weights are not normalized, what we can always do is we just sum up all the weights and divide each weight by the sum of all the weights, and then they're normalized. So this is what you can do. And there's just some text that I'll go through, or go directly to the essence. If I want to estimate where my robot is now, which is called X bar, it's in fact a weighted average of all of my particles. So I have my particles xi and the corresponding weight, and I take the product of these two and sum them up. And since xi refers to vectors and w is a weight, a scalar, eventually I multiply the scalar with the vector and I sum up these vectors, and eventually I get an average, or a weighted average. And this is the estimate of where my robot could be right now. But I've also said we need to take into account our actions we're taking. So we have a motion that we want to take, for example, move forward 10 meters or rotate, whatever. We do this and we apply this action to all the particles, using these error terms that come from a normal distribution. Then we take a measurement update by an outward-looking sensor, for example, a sonar. And the sonar measures how far the wall or the nearest object is from the robot. And we do a measurement update of our particles. I'll show you the equation very soon. And then we normalize the weights, and then we resample. And by resampling, we most likely want to keep the most likely particles and eliminate the particles that have the lowest probability. And then we copy the most likely ones. So this is one approach of how we can do resampling. And in total, we want to keep 100 particles. A few guidelines. This is what we've seen before, that if we just keep moving and moving with our particles, the errors will spread more and more. And we want to avoid this because we want to do some measurement update. And with a measurement, like from a sonar, we get a distance. If you don't have a sonar in your robot, you can use other techniques for a measurement. For example, you can use your camera for a depth measurement. I've talked about this last week in the Outlook chapter, where I've discussed with you depth estimation. You can use 2 cameras for depth estimation. If your robot only has 1, you could mount 1 more camera on top. Some students have done this in the past. However, you could also use a deep neural network, and a trained deep neural network can also allow you to do depth estimation just from single images, given that the neural network was trained on a sufficiently large training set. And I told you for the training set, we actually have a label per pixel, which represents the depth, so the distance. And then you could also predict something like this, and you could use a deep neural network for depth estimation. And your depth estimation or your depth measurement, so it can be a measurement from a sonar, but you could also have this depth estimation from a neural network, for example, or from a stereo vision approach, whatever. This would be your measurement update, or you would have your measurement update Z, and then you need to model of how likely that measurement update Z given your pixel is. And if your particle, if your particle looks in the right direction and has an adequate distance and you take that measurement, then probably this probability would be very high. However, if your particle is totally rotated or much closer to the wall or an object or much further away, then this probability here would be very low. And you would multiply the weight of a particle with this probability of the measurement given your particle, and you would update the weight like this. And after that, you would then normalize your weights. And I've said this before, if your weights don't add up to 1, you can normalize, and you normalize simply by dividing each weight by the sum of all the weights. And like this, you have normalized, so they add up to 1. And then you need to do resampling. And you can either implement your own resampling technique, or there are all sorts of Python libraries that allow you to do resampling. Probably you have seen some of them if you have done machine learning. There are also resampling libraries for data sets, but you can also do resampling on your particles. There's all sorts of techniques. You can work with the cumulative probability distribution of the particles. You can use a resampling wheel. There are all sorts of techniques, but for now, just use a library that allows you to resample objects based on a probability, and try out different approaches in case you implement this and you're fine. And then this is a loop because we're taking a motion update. Our robot moves or rotates. We apply this motion to all the particles. Then we do a measurement update. what we have just seen, that we update the weights of how likely those measurements are for those particles. We normalize the weights, and then we resample. And then we take another action, and we do all of these steps again. And this is exactly what you have seen in this video from before. And these particle filters are extremely helpful for estimating the state of a robot. The advantage of a particle filter is it's super easy to implement. The only work that is maybe a little bit more tricky for you is the resampling, but you can just use a library for resampling. But all the other things isn't too much code. And the particle filter runs very quickly, also on an edge device like a robot. The only issue is taking the measurement. If you use a sonar, it's computationally cheap. If you don't have a sonar, maybe use a second camera or do depth estimation with a neural network. That would be a little bit more expensive, but can also be done on your edge device if you do it right. And then you update these weights, you normalize. This is super easy to do, and you resample. And now you wonder, what's the difference to a Kalman filter? It's two techniques that address totally different purposes. You could obviously use a Kalman filter for estimating the robot's state. That's fine, but probably it's computationally more expensive to use the Kalman filter. In practice, you would often use a particle filter for estimating the robot state, and you would maybe use a Kalman filter for tracking some objects. So if your robot wants to track some other object, maybe for that you would be rather using a Kalman filter then. But they're both two approaches to doing filtering with their own pros and cons. So that's it about particle filters and localizing in a map. The only challenge is you need to know the map. And so far, we've always assumed we have the map and we put the robot in that map. But in a real world setting, maybe you don't know the map and you want the robot to learn the map. Imagine you have a mobile cleaning robot. So a robot that cleans your house, and you don't want to predefine the map. Rather, you want the robot to put in your room or in your apartment, and you want it to work. So it needs to learn the map of your apartment on its own. Plus, it also needs to find out where it is on the map. And that's something that we call simultaneous localization and mapping. This is something that has made, in terms of theory, great progress in the late 90s, early 2000s, in short, SLAM. And SLAM gives autonomous robots major advantages because they can learn a map based on sensors on their own, and they can localize in parallel where they are in the map. It's probably one of the greatest breakthroughs in mobile robotics in the last few decades, and it helped the field of mobile robotics to advance quite a lot. So you're building a map incrementally, and you're localizing where you are in the map while the map grows and gradually becomes better. Again, there's a video in the Udacity course, which I will show, but not record right now. So the recording will be paused again. And welcome back to the recording. Feel free to watch the Udacity video on your own and hear what Sebastian Thrun says. A few years ago, there was a student in this computer vision course who actually implemented SLAM on his own. So it's certainly doable. It's maybe one of the more advanced project topics, but if you're curious about SLAM, feel free to do this on your own. As you have noticed, we are now done with the content of this course. We have started initially with pixel images and filters, then we looked at regions of images and segmented. We built more complex feature detectors like the Harris corner detector. We aimed to recognize objects, and we saw that neural networks, in particular convolutional neural networks, are super helpful to do this, but there are also other approaches. And convolutional neural networks are not in general better. We've also seen how we can process image sequences, for example, using a Kalman filter, using the optical flow or other techniques. And we've seen some more advanced topics like vision transformers, generative adversarial networks, 3D vision. And today we've seen the foundation of mobile robotics in case you want to do a robot vision project. Now I'll say a few things about the projects. Now about half of the term has passed. We have all the theory we need. And for you, it's now time to start working on your projects. Next week, we will still have a lecture, but it's a shorter lecture, and there will be a guest lecture from MVTech. And I want you to be joining the live lecture. Usual time next week, 12:15. MVTech will join online through the Zoom session and present some of they will present some computer vision problems and how they address them with their professional software. So they offer their own software, which is not open source, but addresses problems specifically coming from industry. And if you like the MVTech software, we also have a campus license. Maybe you want to be using MVTech software for your projects, which is totally optional, but maybe you will find some helpful features they have if you want, but they will present next week. We will be recording the guest lecture next week, but the recording will only be available internally in our internal cloud, and it will not be publicly available, unfortunately. But this was the wish from MVTech, and I'll upload it internally to Nextcloud, and all the students taking the course in Deggendorf can watch the recording. However, I would be happy if you join the live session. And then in 2 weeks' time from now, there's a public holiday. And in 3 weeks, which is May the 16th, I want you to present your project proposal. I've already sent a message about this in iLearn. It's just a very quick presentation, 1 or 2 minutes, and just, like 2 slides or something, what you want to investigate in your project. And then if you have any questions, and I will give you some feedback on the proposal. After that, you need to submit the proposal via iLearn after I approve it, but you've seen already the round messages, the messages I've sent. And most of the workload of this course lies in the projects. And the projects will be examined at the end of the term, the beginning of July. I have also communicated the dates in iLearn. Concretely, that's the weekend, July the 6th and 7th, so Saturday and Sunday. And you need to be on campus for this. So this only takes place on campus. In the meantime, if you have any questions, if you need any help with your project or you want to discuss something, I'm available. Just get in touch during the week and we can meet or exchange via email or meet via video call, whatever. So there will not be a weekly session, but you will just get in touch if you have problems. And we will meet, as I said, in 3 weeks when you present your proposal, and that's absolutely mandatory to be present there. And your projects will be groups of 3 to 4 students, so not 2, not 1, not 5. It's 3 to 4, that's fixed. And your project needs to be on a topic relate something on computer vision. It can be about robots, robot vision, or not. This is your choice. And you've had a chance to pick the robots a few weeks ago. And you will present your proposal in 3 weeks. And there will also be a mark eventually on your project, because that's the mark of the course. You can score in total 50 points for your project when you present it in July. You will get up to 5 points for the motivation of your project. So you will present briefly why you're working on this and why it's interesting. These presentations for the whole group will take 15 minutes. So 3 to 4 students in total have 15 minutes. You will present the methodology or the theoretical background of what you're doing in your project. You will present a demo. You will present the lessons learned. Lessons learned means something didn't work out the way you expected or something worked out as expected. And after the 15 minutes, there will be a 5-minute Q&A session in which I may ask some questions or the other students. And in total, you get 50 points, and 50 points are converted into a mark. 50 points is a 1.0, the best mark. 49 points is a 1.1, but this mark doesn't exist, so it's converted to a 1.0. We always round to your advantage. 47 would be a 1.3, that's a valid mark. 44 would be a 1.6, still converted to 1.3. 43 is a 1.7, and so forth. And you need 20 out of 50 points to pass. The conversion equation is here. And in 3 weeks, you would simply present your proposal very, very briefly. The proposal will not be marked, but just stick with 1 or 2 minutes for the proposal, because we have a lot of groups, maybe 50 to 60 groups. So I also want us to make sure that everyone has a chance to present during that time slot. Now I want to know from you if you have any questions about the projects. If you have, maybe raise your hand or just turn on your microphone or send a question here in the chat.
I have a question.
Yes.
What is different for master students that take this as an elective?
Yeah, some master students take this. Here, the challenge is that I want you to pick a little bit more of an advanced topic, maybe not just a very foundation topic, just a project that is a little bit tougher. And that's the requirement for the students picking this as a master student.
Okay, but there are no like clear guidelines on how tough it should be or something like that?
We will
or
discuss
in
this
which
when you
direction?
present your project
Okay.
proposal. You would just say that you are one of those master students taking this as an elective, and then I would give you feedback on this.
Okay, thank you.
But it doesn't need to be infinitely difficult for the master students, maybe just some more workload, because that's what is expected.
Yeah.
And the project proposal presentations, they will take place here via Zoom. So all of us will be in the Zoom session, and then each group will give their proposal one after another. So project proposals are online here in Zoom, and the presentations of the projects in July are only on campus. Okay, next one.
Yeah, for me, I had a question we were interested in doing, like, do you have to train a model, or can we just use a already existing model and just make a project that works, kind of?
This is up to you. Obviously, it should be more than just downloading a pre-trained model and adding 2 lines of code. So it still needs to be substantial work, but you are welcome to use a pre-trained model for your use case, or maybe continue or do fine-tuning based on your data. But there's nothing wrong with using a pre-trained model.
Okay, thank you.
Any other questions? So I saw one student turn on his mic, but I don't hear you.
Hello.
Yeah.
Are we supposed to use neural networks and train something, or can we use OpenCV or something a bit simpler to do our project?
This
Is
is
it
totally
supposed to
up to
be?
you. You can pick the tools and project as you wish. The projects don't have to be related to neural networks. There's lots of other vision stuff as well. So this is up to you, as well as which tools you pick.
Okay, thank you.
And a student asked in the chat, what if I reject the project? If this really happened, you would just send a new proposal a few days later. But the best way to not have your proposal rejected is just don't pick a super simple project, because if you say, all I want is, I only implement, the Sobel operator, or I use a pre-trained model and I add 2 lines of code, that will definitely be rejected. So just pick a sufficiently complex project, and that's probably the best way of not having it rejected. Yes, there's another hand raised.
Yeah, could you also explain what you mean with methodology, or what do you mean with methodology?
Yeah, just the theory. So imagine you're building some tracking app that tracks, I don't know, a burglar or something. You would just briefly explain which theory you have picked. If you have picked a Kalman filter, just provide the essence. If you have picked a totally different method that we don't know, explain it in greater detail, or maybe which technologies you have used, something like this.
Okay.
And the demo should be live. Sometimes there are some students, once I had some students, they build an AI to play pool at home or something. In such cases, a video would be acceptable for the demo, but typically I want a live demo and not just a video. However, you can record a video maybe as a backup in case there is some issue with the live demo that suddenly your robot dies or something. Ideally, live demo, if you have a recording as a backup, or if you're just unable to provide a live demo, then that's also okay. So if there are more questions, just raise your hand. Otherwise, I'll close the session soon. Yeah, you're well. We got this here in the chat. You're welcome to use any hardware to train models. If you need access to servers or GPUs, get in touch with Mr. Runkel, the one from which you got the robots. He's in charge of the deep learning lab, so he has more hardware available, but you can use much more than just that robot, because that robot GPU won't be very helpful for training, I guess. So, and with there not being any further questions, we're done for today. And I look forward to seeing all of you at the guest lecture of MVTech next week. And then I will see you in 3 weeks at the proposal presentations. Have a good afternoon. Bye-bye.